Hello everyone, I'm Dev, a PhD student in cognitive science at UCSD. This work is done in collaboration with Professor Daniel Wigdor from University of Toronto and my advisor, Professor Haijun. Computer programs are hard to understand. Say I'm a programmer and I come across this piece of JavaScript code that sorts an array. And naturally, I want to understand how it works. Well, I have a few options. I can continue to stare at the code, but that won't get me very far, especially because I don't remember the merge sort algorithm it implements off the top of my head. Instead, what I might do is turn to a tool that lets me step through the code's execution to see how values of variables update. This can be a traditional debugger or something graphical. As an example of one of these tools, I'll use Python Tutor. So here I'm stepping through the code and seeing the state update on the right-hand side of the screen. As I'm stepping through it, I can answer a simple question, like what's the value of a variable at a certain line, but for more abstract questions, like how does the code as a whole work, I'd have to sit here for a while and synthesize each little step into a coherent picture. And so these tools are at a low level. They give you all the details, but leave it up to you to put those details together. For a high-level view of how merge sort works, I might turn to a YouTube video or a textbook that uses simplified visualizations designed specifically to explain that algorithm. And so we have two kinds of visualizations: low-level ones that work for many programs, and high-level ones that are specifically designed and only work for one algorithm at a time. This gap in abstraction is a problem because as programmers, we don't just think about code at one level of abstraction. We may read code bottom up, or we start with an overall hypothesis and incrementally refine it. So we think about code at many levels of abstraction, but the tools we have to inspect program behavior exist at a single low level. Can we design a tool that lets us look at program execution across multiple levels of abstraction? To address this question, we designed CrossCode, a visualization system for a subset of JavaScript that takes advantage of the intrinsic features of a program, such as its syntactic structures, control flow, and data flow, to provide a flexible representation of its execution. Instead of navigating line by line, CrossCode groups operations based on the syntax tree. It then renders these changes in data through animations, traces, and color encodings. Let's look at it in action. Here I have code that sums elements in a list. CrossCode creates a view of its control flow, as well as of the data. I can interact with the control flow view to navigate across program execution, and I can break down any one of these steps into smaller steps. With that in mind, let's revisit our merge sort example from earlier. For context, merge sort takes an unsorted list as input and returns a sorted list. It does this by recursively dividing the original list into two halves and then merging those sublists together in ascending order. Let's take a look at this merge sort code through CrossCode. We can jump into the merge sort call by clicking on it and step through each of its substeps. It looks like we first split the array into two parts. Let's take a look at how that split is done by breaking down the for loop. Okay, so I put the first half of the list into a left sublist and the second half into a right sublist. After the loop, we sort each of those sublists recursively. And finally, we merge those sorted parts together, which is what we return. Let's take a look at how that merge at the end is performed. Here, I'll use a compact form of the loop so I can get an overview of it. Okay, so we have two indices, I and j, that store the current index we're at in each of the sublists. And at each iteration, we just pick the smallest element from the two lists to create the final sorted merged lists. So in about a minute, we were able to get the gist of this algorithm that might have taken a lot longer if we were just stepping through it with a line-by-line debugger. Let's take a look at one more example. This time we have code that doesn't work, and we will debug it with CrossCode. This function is supposed to compute the nth Fibonacci number, but it returns null, which is not ideal. And just as a reminder, the nth Fibonacci number is just the sum of the prior two numbers in a sequence. Here we will assume that our sequence starts with the numbers 0 and 1. Okay, let's see why it returns null by jumping in to the Fibonacci function call. Well, this loop seems to just consider the number 1, and then it returns null. Let's go to the first iteration of the loop. And indeed, it just looks at 1 instead of looking at 0 and 1. So we can fix that sum in the source code. And this time, the sequence is generated correctly, but we still return null. Why is that? Oh, it's because it's returning the index at 7, but the indexing of first starts from 0, so it should be -1. And now it works. I hope those two examples gave you some intuition for what CrossCode does. Let's take a look at how it works. The execution of code can be modeled as atomic steps. These can be things like storing temporary values in registers or binding a variable name in scope. In CrossCode, we group these sequences of atomic steps into aggregate steps based on the program's syntax tree. This way, I can query based on the code's syntax. I can ask, what is the effect of this if statement as a whole? And for further details, what is the effect of this variable declaration inside the if statement? But repetitive operations, like long loops, can still get out of hand and hard to navigate even if you chunk things by syntax. CrossCode uses two mechanisms, abbreviations and compact forms, to help with this. Abbreviations trim the amount of repetitive information by collapsing a step into a dot, potentially grouped with other dots. These are interactive and can be ungrouped as well as unabbreviated. Nested function calls can also be abbreviated, which makes it feasible to browse deeply nested recursive functions. Steps can also be viewed in a more zoomed out representation that take up less space. And both abbreviations and compact forms are applied proactively to gradually reveal more information and to hide older information. All these techniques can work together to make computer programs more understandable, debuggable, and learnable. To that end, the design decisions in CrossCode are guided by three key patterns that we observed in handmade diagrams and animations. One, that operations should be aggregated into key steps, which are like the milestones of an algorithm. In CrossCode, we assume these milestones to be captured by syntax. Two, repetitive operations should be abbreviated. Doing so enables viewers to observe just enough instances of a pattern to induct the general rule behind it without being overwhelmed by every single instance. CrossCode abbreviates linear loops and nested function calls. 3. An overview should be provided of the execution steps. This helps to add context to a step and synthesize overall patterns in program behavior. In an exploratory study comparing CrossCode against Python Tutor and freehand drawing, we find benefits of CrossCode to debugging, understanding, and as an instructional visual aid. I wish I had more time to talk about the results and the overall design of CrossCode, but I hope that this piqued your interest, and I encourage you to check out the manuscript for more details. Thank you again to my collaborators, as well as to the anonymous reviewers whose feedback helped shape this work. Thank you.